All right. Again, this is a return to long form videos where I work through my entire thought process for the problems. And please pause and rewind the video as necessary. And aside from that, I'm just going to jump right into it. I do usually check the final sentence to see what the question is asking me, just to help me make my list a little bit easier. The thrower takes 1 second. Wow, I'm putting that in my list immediately. 1 second. Starting from rest, so the initial velocity is 0. And because these are all angular, I know that the initial angular velocity is 0. What will be the speed of the discus at release? So we're trying to find how fast they throw it. To throw a discus, a person throws it with an outstretched arm, or throws the discus with an outstretched arm. And for those of you guys that aren't into track, discus is where they throw the giant disc. Starting from rest, begins turn with a constant angular acceleration, so there is an angular acceleration. He releases it after 1 revolution, 1 complete revolution. So that's the angular displacement, or rather the final angular position of 1 rev, and I'm going to assume that the initial angular position is always 0 because that works for my brain. And if you wanted to, I don't think it's ever a bad idea to start your list with theta naught theta, omega naught omega, alpha and t. That way you don't forget anything. And I am missing the final angular position. In fact, I'll probably do the rest of my problems just starting off with a list like that before I get into it. We know the diameter of the circle. The diameter is 1.8 meters, which means that the radius is 0.9 meters, or half of the diameter. What will be so we're trying to find the final angular speed. And then we're going to our kinematic equations. This is a straight kinematic problem. And anytime I see revolutions, I'm immediately converting them to radians. So we know we have 2 pi, and again, I'm going to do this in every problem I do, 6.28 radians is 1 revolution. So now we can cancel out revolutions, and he completes 6.28 radians. And now my list is pretty complete. We can calculate the angular velocity, but all of the equations have acceleration in them, all 3 of them, which means if we're trying to find final velocity and acceleration is unknown, we're going to have to solve for that first. That's also a quick little tool for you to have, is if you don't have acceleration, you're probably going to have to solve for that first if they ask you to solve for something else. So I'm going to use the second equation, I think. Theta equals theta naught plus omega naught t, because we know that, plus 1/2 alpha t squared. Alpha is unknown, but the initial velocity is 0. The initial position is 0. And the final position is 6.28 radians times 1/2 times alpha, which we're trying to solve for, times time, which is 1 second, but that gets squared. Don't forget to square it, even though it doesn't affect it in this problem. So basically 6.28 times 2, which is 12.56 radians per second. And again, I don't usually round until I get to the very end of whatever they're asking me to solve for. And then we can plug that into the first equation, solve for the final velocity, omega equals omega naught plus alpha t. And from this point, it's basic algebra and plug and chug. So that times the time of 1 second, which is going to give you 12.56 radians per second. And let me double check and see if I made a mistake anywhere. I definitely did make a mistake. They asked for what is the speed of the discus. If they ask for the speed, they're asking for the linear speed, not the rotational speed. But we did have to solve for that. But we can do that using the Vromega equation. I should have paid much closer attention. I even read the question before I started and still forgot. Velocity is Vromega. So the radius of 0.9 times that angular velocity of 12.56 radians per second. And that should give you 11.3 meters per second. So please be cautious, and I'll try to do a better job being cautious myself moving forward. This is just glancing at another kinematics problem. So let's read it. Computer hard disk starts from rest, then speeds up with an angular acceleration of this speed until it reaches a final angular speed of this. And then they ask how many revolutions has the disk made in 10 total seconds after it starts up. So this is a two-phase question. You always have to be on the lookout for these. So we have two phases. And the reason you have to pay attention to different phases is because your three kinematic equations are only true if acceleration is constant. And in this problem, the acceleration is not constant. That's what I mean by phases. Phases of acceleration. So we would have to use those kinematic equations for phase 1 when it's spinning up, and then phase 2 when it's already reached its max speed of 7,200 RPM. So this is when it's spinning up, and this is when it's already at constant speed. Fantastic. So now that we know that during phase 1, we know that the initial position is 0. We know the final position is unknown. That's really what we're trying to solve for. And I think what I'm going to do is find how far it spins up during phase 1 and how far it spins up during phase 2 and add those two positions together. And I'll show you the two different ways that you can approach this. We know that the initial angular velocity is 0 during phase 1. The final angular velocity, is 7,200 RPM, or revolutions per minute. And if you want help converting these units, I would go back to the previous set because I did show you how to do that in the second or third question. But basically, you multiply by 6.28 and then divide by 60. Or, if you were paying attention to what I said, if you know you're going from revolutions per minute to radians per second, because that shows up so frequently, multiply it by wild 104.7, and that will tell you how many you have. And that's a shortcut that you shouldn't do unless you feel very comfortable. But if you're not comfortable with this, you should do it the old-fashioned way. Regardless of how you do it, you should get just about 754 radians per second. You might be a little high or a little low, but that's about what you're getting for the final angular velocity. We don't know what the acceleration is, but we know it's constant, and we don't know the time for it either. And we also know that we have 10 seconds total between the two phases. So we don't know how much time is during phase 1 and how much time is during phase 2, but I feel like that's going to become important. So during phase 1, we are trying to find the angular displacement, but since we don't have acceleration, I am going to find that first, just like I said in problem number 1. So we're going to the first equation, omega equals omega naught plus alpha t, because we know final, initial, and, oh, we don't know time. Oh, no. Oh, but we do, no, we don't know. Oh, we do know alpha. It's 190. I forgot to write that down. Okay. And I'm so glad it's already in radians per second per second. Okay. And let's change colors. So we're getting up to 754. We're starting at 0. So 754 equals 190t. Fantastic. Now we know how much time is during phase 1. So 754 divided by 190 is 3.97 seconds, which means that our time for phase 2, if there's 10 seconds total, time for phase 2 would be 10 minus that number, and I'm going to write that in right now, is 6.03 seconds. That, I think, is the trickiest part of this problem by far. So let's figure out how many radians it did during phase 1 using the second equation. The initial velocity is 0, the initial position is 0, and we're left with 1/2 alpha t squared. And if you just do a little bit of basic algebra and plug things in and solve, you can get 190 times 3.97 squared. Don't forget to square it. Don't ever forget to square it. Roughly 1,500. And because this is my key, I am going to be more precise and not round it. 1,497 radians. And you shouldn't either. There's no need to round. It takes 2 more seconds to write the actual digits. So that's our total displacement during phase 1. Now, I said you had 2 ways of approaching this, but you don't want to add the distance from phase 1 twice. So I can just remember, hey, this is my distance from phase 1. I need to remember to add this at the end of phase 2, or when you plug it into the second equation, theta equals theta naught plus omega naught t plus 1/2 alpha t squared during phase 2, because again, everything to the right of this column means during phase 2. Or you can put 1497 in here and say, hey, we've already reached that. So during phase 2, we've already started with that. So you can either put this into 0 and add it at the end, or you can put it into for theta naught and just solve it. I'm actually going to do it this way, but just remember, hey, you already put it in. And I'm going to make a note for myself. You already added theta from phase 1, the angular displacement from phase 1. The initial velocity during phase 2 is the final velocity from phase 1, right? Because if it spins up to this speed at 3.97 seconds, it's already hit 7,200 RPM or 754 radians per second. So 754 times the time for phase 2, which is 6.03. And I think that's the biggest. There's a lot that you have to be very careful with in two-phase problems. So please just take your time, think about it conceptually, think about, okay, the final of this is the initial of this. If we've used this much time, then that much time gets taken away from phase 2. Just always being cautious. Ooh, it's a constant speed during phase 2, which means the alpha of phase 2 is 0. That's fantastic. So we can ignore that third term completely. So 1497 plus 754 times 6.03 is going to give us 6,044. Or I'm going to round it to 3 sig figs, 6,040 radians. And let me make sure that I answered the question. How many revolutions? I did not answer it. How many revolutions? Well, 2 pi radians, or 6.28 radians, is equal to 1 meter. Is that right? No, 1 rev. Sorry, 1 revolution is 6.28 radians. Goodness gracious. So 6040 divided by 6.28 is 962. So it has completed 962 revolutions, and that's the total displacement, which that's what the answer key says. I agree. All right, number 3. Crankshaft in a race car goes from 3,000 RPM, goes from rest, so there's our initial velocity, to this angular velocity in this time. So again, we're looking at kinematics. Theta naught, theta, omega naught, omega, alpha, and time. The initial position is 0. The initial angular velocity is 0. Time is 2 seconds. The final velocity is 3,000 revolutions per minute. And I'm going to do my 1047 trick. And if you're not comfortable with that, make sure you're converting units using the old-fashioned way, and make sure that you remember, hey, this goes from RPM to radians per second. And if you don't feel comfortable with that, please do it the old-fashioned way, but you will get the same answer. And I get just about 314 radians per second. Fantastic. We don't know the acceleration, but that's what we're solving for in part 1. And we don't know how many revolutions, but or the final displacement. Ooh, I'm going to circle revolutions, so I know I need to convert that. And always go back and check the question to make sure you answered the question. That'll save you so many accidental, unnecessary mistakes. So let's find the acceleration. Well, we know final velocity, initial velocity, and time. We can use that first equation. Omega equals omega naught plus alpha t. So 314 equals alpha times 2. So basically, 314 divided by 2 is going to give us 157 radians per second per second. Radians per second. And hey, that's our key for A. B is how many revolutions. So we're trying to find the final angular position or the total angular displacement. So theta equals, well, theta naught's 0. I won't skip that. Plus omega naught t, but it started from rest, so that's going to collapse to 0. So we're left with 1/2 alpha t squared. And if you've become comfortable with kinematic equations at this point, you don't even have to write these in. It's not a bad idea, but you can save yourself some time if you're trying to. We know alpha from phase 1 is 157, and we know time is 2, but don't ever forget that squared. I'll say it every time I do this. So 0.5 times 4 times 157 should give you 357 radians. Wow. But they didn't ask for that. They said how many revolutions. So radians to revolutions, how many rads equals how many revs? Well, 1 rev is equal to 6.28 radians, or 2 pi radians. So 314. Whoa, 314. Did I write the wrong answer? I did. That should be 300. Yes, I got the 57 from this. So that should have been 314. I copied it wrong. I'm so glad they asked us to do that last part. 314 radians divided by 6.28 should give you, oh wow, exactly 50. I get 50.0 radians, which the answer key agrees. Fantastic. All right, next problem, number 7. We're finally finishing. We finished kinematics, and now we have a pulley. And I see forces, which immediately makes me think force and or torque. And that's what the question is. What is the net torque about the axle and the pulley? About the axle on the pulley. So I see 2 rotational forces, or 2 torques acting on this. This one's trying to rotate it counterclockwise, right? It's trying to rotate the wheel this way, which means that's going to create a positive torque. And this one's trying to create it clockwise, which is going to create a negative torque. And the net torque is the sum of all torques. So I'm just going to add the 2 torques. And to do that, our equation for torque is RF, because the further out you are from the center of rotation, the more torque you're going to get, and the more force you push with, the more force you're going to get. Don't forget sine theta. But if theta is 90 degrees, meaning the radial arm is perpendicular to the force, then 100% of your torque is being used, or 100% of your force is being used to create torque. So you can do the torque of this guy plus the torque of this guy. I'm going to do it in one line. I'm going to call this F1 and this F2. So torque 1 plus torque 2 equals my net torque. And I am going to put my positives and negatives in every time I put in net torque. And this one's also a 90-degree angle. And sine of 90 equals 1, right? Because 100% of our force is being used to create torque. So it's multiplied by 1. We haven't lost any from pulling at an angle or pushing at an angle. So I'm going to fill in my positives and negatives. Torque 1 is going to be positive. Torque 2 is going to be negative because it's trying to rotate the wheel counterclockwise. Right? This force is pulling it this way. So torque 1 is R1 F1, minus R2 F2. And, we haven't converted our radius. This is a diameter, which means the radius is going to be 2 centimeters. But we don't ever want it in centimeters, so I'm immediately going to divide it by 100 because 100 cents in a dollar, and you get 0.02 meters is our radius. And that's the same radius for both of them, which makes R1 and R2 super easy. So 0.02 times F1, which is 20, minus 0.02 times F2, which is 30. 30, because I already put my negative sign in here. So don't double negative. Basically, the torque is negative. And I guess I shouldn't have put those pluses and minuses in front of the numbers. That's something I'll be more careful of in the future. But then at this point, just multiply them through and add them, or in this case, subtract them. So 0.02 times 20 minus 0.02 times 30. And that should give you negative 0.2? Negative 0.2 is correct. I copied the answer from the key wrong, but that's the right answer. Number 12. What is the net torque of the bar shown in this figure about the axis? So this is our axis of rotation. We want to find the net torque. We have two forces. And it looks like they both have the same radial arm of 0.75 meters. And we want to find the total torque because net torque is the sum of all other torques. So I'm just going to call this torque 1 and this torque 2. And this one is going to rotate it counterclockwise, so that's going to be positive. And this one is parallel to it, and I don't know if that's going to be positive or negative. I'm not sure. But we'll find out very shortly. So now, again, remember that your equation is not just RF, but RF sine theta. And if it's not perpendicular, don't forget your sine theta. In fact, don't ever forget your sine theta, and you won't make the mistake of forgetting it. So RF sine theta, where radius is 0.75 for both of them. F1 is 10, and it is positive, times sine 90, which is 1, plus 0.75 for the radial arm of 2, times 8, but it's perpendicular, so it's going to be sine 90, or parallel, so it's going to be sine 90, which is 0. Sine 0, because they're parallel. Sine 90 is 0. Which makes sense because the force is completely out. A torque is a rotating force. In case you haven't heard me say it that way, a torque is a rotating force. So it's a force that will cause rotation. If you're pulling it straight out, you're not rotating this board at all. So it's contributing 0 torque. So it's just going to be 0.75 times 10, which is going to be positive 7.5 Newton meters. I don't know why the key says negative 7.5. Maybe I copied that one wrong too. Nope, that is correct. I used a key from a different year where they changed the direction of the force. So it is positive 0.75 Newton meters. 13, what is the net torque of the bar shown in the figure below about the axis? Super easy. Torque 1, torque 2, and then just net torque is the sum of other torques. So T1 plus T2, and then I'm going to fill in my signs, which one's positive, which one's negative. This one's rotating it clockwise, which means it's going to be a negative torque. And torque 2 is going to try to rotate it counterclockwise, which is positive. That's standard. And then just plug in RF sine theta, but they're both perpendicular. This is your radial arm. This is your force. They're perpendicular. They're both perpendicular to the radial arm, which means we can ignore sine theta. because 100% of the force is being used to rotate it. So then negative RF is negative 0.25 for the first one. For the radial arm, the force is 8. And then for the second one, 0.75 times 10. So negative 2 plus 7.5 is going to give us positive 5.5 Newton meters. And yeah, that checks out with what I wrote from the key. And I am going to write net torque in there. Fantastic. 5, rank the torques in order from smallest to largest. And I'm just going to figure out what the torque is in terms of R and F. Oh, we're also given different masses, but the torque equation is RF sine theta, which means mass doesn't change the torque. So the first one, we have R times F times sine theta, but it's perpendicular, which means we can ignore sine theta for all of them. So 1 is RF, 2 is R times 2F, so 2 RF. For the third one, it's 2R times F, which is still going to be 2RF. And for the fourth one, it's 2R times 2F, which is going to be 4RF. Well, that makes it very easy to rank. We have 1, 2, 2, 4. So this one is greater than, this one is less than, which is equal to this, which is less than this. It's already in order. Torque 1 is less than 2, is equal to 3, is less than 4, 14, and that is what the key says, so that checks. Oh, now we are given angles, and remember, it's always the angle between the radial arm and the force, and they did draw the correct angle for us to make it a little bit easier. So let's do the math on this. What's the net torque? That's straightforward. Same thing we've done for all of these. Figure out the torques and then figure it out. Torque 1 plus torque 2. And I'm going to call the one on the left 1 and the one on the right 2. And it's going to be RF sine theta. But don't forget your positives and negatives. This one's trying to rotate it clockwise, so that one's going to be positive. And this one's, clockwise is negative. Excuse me. And torque 2 is trying to rotate it counterclockwise, which is positive. So negative R1 F1 sine theta plus R2 F2 sine theta. At this point, it becomes very plug and chug. So negative 0.25 times 8 times sine 40, because it's the angle between the radial arm and the force, plus 0.75 times 10 sine 30, and then I'm just going to plug that into my calculator, and when I do that I get 2.46 Newton meters, which checks out with the answer key. And that's our total torque, or our net torque. 15. 15 is a center of gravity problem. And for this, you kind of need to know the center of gravity equation. The center of gravity, or the cog, if you will, it's basically, it's a torque problem for all intents and purposes, but you divide out the total mass at the end. And you can choose your pivot point wherever you want. For me, I find it easiest to always choose the leftmost end as the 0 marker, and any radius from there is measured from that point. But you could have chosen anywhere else, but it can cause some confusion. And they did say how far from the left end, so that means we won't have to subtract anything at the end. But your net torque equation is the sum of all torques, and if it's balanced, I think that's a bad way of explaining it. I'm not going to explain it that way. But your torque, your center of gravity equation, I'll do it this way. is the radius 1 times m1 plus radius times m2, and so on and so forth, which looks very similar to your torque equation, divided by the total mass. And the reason this equation works to figure out the total distance is if you have 10 kilograms here, and it's a massless bar, which it is for this first one. Ignore the weight of the bar itself. It is the torque equation. So rate RF plus so on and so forth for all of the torques. Well, the force is the force of gravity, which is equal to mg. So it figures out how much weight is distributed at this position and how much weight is distributed at this position. But in the end, we just want the final position. So we basically divide out mg from all of it. But g is going to be the same here and the same here and the same here, which means it cancels from all of them. And then you're left with rm plus, well, just m in the denominator. So it's the sum of RMs divided by the total mass. So it's really not that involved of an equation, but it is something that you do need to know. And now we can just plug them in. Well, again, we always need a good diagram. We have a 35 kilogram weight here and a 20 kilogram weight here. I swapped them. This should be 35 and the one on the left should be 20. So for the first one, and I'm going to call this 1 and this 2 because labeling is always a good idea. And I'm going to erase that erratic 10 just so it doesn't look confusing. 20 is the mass of the first one, and the radius of the first one is, well, how far is it from the pivot point that we chose? You get to choose your pivot point in all torque equations. It's just much easier if you choose it at the actual point of rotation. Well, it's no distance from there. So if we're choosing this as our pivot point, this doesn't extend out the center of mass from that point at all, or the center of gravity from that point at all. And we're going to do the same for the second one, except this one is at the full length of the bar. Oopsie daisy. And we know the full length of the bar is 1.7 meters. So 1.7 times the mass hanging from the other end, which is 35, divided by the total mass, which is 20, and 35, which is 55. This becomes 0. And this becomes 1.7 times 35, which, if you're working along with me, is about 60 divided by 55. Should give you... Oh, I accidentally pushed an extra answer in there. Give me 1 second to fix that. Divided by 55. 1.08 meters from the left end. So there-ish. Wait, 1.08. Halfway is the 85 centimeter mark, right? 0.85. Yeah, so it's between there and here. This is where the current center of mass is with just the barbells. Now, for part 2, where is the center of gravity if the 8 kilogram mass is taken into account? Well, that's the mass of the bar, and anytime the bar has a mass, it's this part's pulling down as much as this part's being pulled down, and this part's being pulled down as much as this part's being pulled down. So you can average the center of the force, or where the force of the bar is, and say, hey, you know what? We're just going to say 100% of the mass, 100% of the weight is dead center at that 85 centimeter mark. So we're just, for part B, we're just going to repeat that equation, but with this. And notice, this was our previous center of mass, right? Whoopsie daisy. This was our previous center of mass. So if we're adding more mass here, that's going to bring the center of mass to the left. But we still will plug it in, 0 times 20, because I'm still going from the left. and plus 8 kilograms times 0.85. I think, let me double check to make sure 1.7 divided by 2 is 0.85. It is. Plus the third mass, which is 35 kilograms, times that radial arm, which is 1.7, divided by the total mass, which is 20 plus 8 plus 35, which is 63 kilograms total. And this will find how much weight is distributed here, here, and divide out the mass. That's where that equation comes from. I know I already said it, but I'm saying it again to try to drill it into you. This term collapses to 0, and at this point it becomes a very basic algebra problem. So 35 times 1.7 divided by the total mass of 63 is 1.05. Which makes sense because we did want to bring the center of mass to the left because we've added mass to the left of where our previous center of mass is. So 1.05 meters is our new center of mass, which I'm going to call COM2. And the answer key said 1.2. That's very clearly wrong because the center of mass would be brought to the left. So the answer should be 1.05. All right, jumping into the final question. Looks like a torque problem just from seeing it. I see Tom and Jerry both pushing on a 3-meter diameter. Ooh, 3-meter diameter, which means 1.5 meters is the radial arm. And this is one that I do think you guys should pay very close attention to, at least for how we calculate the force, especially in part B, or at least how we calculate the angle. The angle is always the angle between the radial arm and theta, which for this is going to be 80 degrees because opposite angles are equal to each other. And for this, opposite angles are equal to each other, so this is going to be a 60-degree angle in here, right? If we have two intersecting lines, this angle will be identical to this angle, and this angle will be identical to this angle. That'll become much more important in part B. Tom pushes with a force of 40 newtons, and Jerry pushes with a force of 35.2 newtons, and I am paying attention to which direction the torques are because they are asking about the net torque. That's what we're trying to find. Tom is pushing it in a counterclockwise rotation, so this one's going to be positive, and Jerry's pushing it a clockwise rotation, which is going to make it negative. So torque Tom plus torque Jerry. Tom is positive, Jerry is negative initially. And then just RF sine theta, R1F, RTFT sine theta minus RJFJ sine theta. And then it's plug and chug at this point. 1.5 times 40 times sine 60 minus 1.5 times 35.2 sine 80. 1.5 times 40, and I'll plug this into a calculator. And when I do that, I get negative. Wow, Tom just barely, wait, no, Jerry just barely edged him out because it's a negative torque. So Jerry just barely wins. That's going to rotate clockwise. 0.0363 Newton meters of torque. So that means it is going to accelerate in the clockwise direction. If it started from rest, it will speed up in the counterclockwise direction. All right, let's do part B, which is the exact same thing, except Jerry, what is the net torque if Jerry reverses the direction he pushes by 180 degrees? So instead of pushing down and to the left, he's going to push up and to the right. And remember, it's RF sine theta. This angle is not 80 degrees anymore. His force is still 35.2, but also he's pushing in the clockwise direction, so this becomes a positive torque. And the angle changes because this is a straight line. We know there's 180 degrees in that half circle. And if we've already used 80 degrees here, that makes this 100 degrees. And I'll explain that again, and I'll erase my lines so that it's a little more clear. And let's change color to orange. So if this is our radial arm and this is our force, I forgot how to do it. 1, 2, 3. Yeah, I can't believe that. That's so good. We're trying to figure out the angle between the radial arm and the force. And if this whole semicircle is 180 degrees, right? Because a whole circle is 360 degrees. Whole circle is 360. This is a half circle, or 180. And we've already used 80 degrees here. That makes this angle 100 degrees. And that really is the extent of the geometry you'll have to do in this class. SOHCAHTOA and being able to figure out 180 minus whatever angle you're given. And as long as you're drawing good diagrams, that becomes super easy. So we have a new angle. We have the same force, but the torque changes direction. And the radial arm is still 1.5. So our equation pretty much is the same. So I'm just going to copy and paste that here and change my sign to positive. Fantastic. So now they're working together. It's definitely going to angularly accelerate. RT. Ooh, we can copy the next line too. Let's do that. Save ourselves a little bit of effort. And our next line too, but make sure you change your angle and your sign. Don't get too crazy with copying things that you forget what you're supposed to do. And this becomes sine 100. And at this point, it becomes very plug and chug. And when I do that, I get 103.95, or exactly what the answer key says, rounded to 3 sig figs, 104 Newton meters. So I hope that helped. And let me know, as always, if you have any questions. And if you stayed to this point, I might as well reward you with a dad joke. What do you call it when the owner of Microsoft gets on an airplane? A bill in air. A bill in air, because Bill Gates. All right. Have a great night. I'll see you in the next one. Goodbye.